Ar jūs norite internete jausti saugiai ir naršyti po beribį tikrą internetą? Jeigu atsakymas yra taip, jums į pagalbą skuba Surfshark VPN. Surfshark VPN leis jums naršyti po visą internetą, kai prisijungsite į svetimą šalį. Pavyzdžiui, tikrai žinau, kad yra buvo tokių situacijų, tada norite pasižiūrėti video YouTube ir jums neleidžia pažiūrėti, nes sakote, jog esate trečioji šaly. Ne bėda, tam yra Surfshark VPN. Persikelsti į Ameriką, Vokietiją, Japoniją ir galėsite laisvai žiūrėti to šalies turinį. Aš žinau, kad yra tokių buvo atvejų, kada norite pažiūrėti per Netflixą kažką, bet negalite rasti, nes nesate toj šaly. Tai irgi prisijungsite ir rasite. Kas yra dar kietas dalykas, jog su Surfshark VPN jūs galite jaustis itin saugiai, nes jie enkriptina jūsų datą ir galite jungtis prie viešojo Wi-Fi'aus be jokios panikos. Jie taip pat blokuoja ir kenksmingus puslapius, tai galite naršyti po visą internetą laisvai ir be varžymų. Su mūsų kodu PVS jūs gausite net 83% nuolaidą ir 3 papildomus mėnesius nemokamą nuolaidą. O jeigu jums nepatiks jų paslaugos, tai žinokit, visada galite pasinaudoti 30 dienų grąžinimo garantiją. Tai skubėkite Surfshark, panaudokit mūsų kodą PVS ir naršykite internete saugiai.
3, 2, 1, 0, and liftoff.
All 3 engines up and burning.
Tranquility Base here. The Eagle has landed.
Iki visi sugrįžę į Space and Time epizodą. Šiandieną mes turim nuostabią temą, nuostabų inžinerinį kūrinį, apie kurį mes norim pakalbėti. Tai yra
James Webb kosminį teleskopą.
Taip.
Tu čia gerai man permetė šitą, kad
Taip.
aš pabaigčiau sakyti.
Nes mes pabaigėm vienas kito. Jo, tai mes norime pakalbėti šiek tiek apie šitą teleskopą, taip pat ne mes kalbėsime, mes turime išgirsti ir NASA inžinierius, kuris prisidėjo prie šitą teleskopą.
Yra second in command,
Taip.
Antras pagal svarbumą žmogus, vienas iš James Webb kosminio teleskopo misijos vadovų, kuris jau greitai išeina į pensiją ir šiaip yra dirbęs prie daugybės fainų misijų.
Tikriausiai, kaip jau supratot, epizodo metu kalbinsim dar vieną NASA inžinierių ir mokslininką. Šiandieną mes kalbinam John Durning, kuris yra James Webb kosminio teleskopo projekto vadovo pavaduotojas. Antras svarbiausias žmogus vadovaujantis visai James Webb misijai. Johnas atliko pagrindinį lyderio vaidmenį visais teleskopo skrydžio techninės ir programinės įrangos kūrimo aspektais. Iš karto perspėjom, jog pokalbis bus anglų kalba, o dėl techninių nesklandumų interviu su Johnu įrašėm iš 2 kartų. Todėl pirmoji pokalbio dalis, kuri truks maždaug apie 15 minučių, bus šiek tiek prastesnės audio kokybės.
O mes kalbėsim apie didžiausią ir galingiausią kosminį teleskopą istorijoje. Tai yra James Webb kosminį teleskopą, kurio dabar vardą lydi kontraversijos. Sužinokite kokios.
Spauskite čia.
Taip, ir gali būti, kad bus pervadintas, kol kas tokių didelių planų nėra. Bet čia yra didžiulė tarptautinė misija, pagrindė NASOs vykdoma, 10 milijardų dolerių vertės, kol kas bent jau. Dar gali išaukti, jeigu jinai tęsis ilgiau negu yra numatyta, tai aišku, ir jos kaštai išauks. Ir paleista, taip.
Aš norėsiu pasakyti, kad truko 20 metų.
Jo, realiai James Webb buvo jau toks ypatingai astronomų bendruomeniai kaip keiksmažodis, toks bairis. Tai kada James Webb leis? Nes jį nuolat nukelinėdavo. Tausime, pirmą kartą turėjo 2000, kokiais, nežinau, 4, bijau pameluot, bet labai seniai jį iškelt ir vis nukelinėdavo ir problemų buvo daug įvairių, bet dažnai viskas atsiremdavo į kaštus, nes NASA yra biudžetinė įstaiga ir senatas turi patvirtinti, kad tikrai duoda tokį biudžetą, o kadangi augo laikas, komanda augo, viskas sudėtingėjo, aišku, ir kaštai, pinigai tuo pačiu, pinigų kiekis didėjo ir tai buvo labai sunku, bet galiausiai praėjusių metų pabaigoje buvo iš Europos kosmoso agentūrai priklausančio kosmodromo Prancūzijos Gvijanoje pakeltas į kosmosą.
Gruodžio 25, jeigu gerai pamenu.
Taip, ir vėl buvo ne iš pirmo karto. Turėjo būti vieną dieną pakeltas, tada gavos, kad kitą pakėlė, bet dabar jis jau yra ten, kur ir turi būti, už 1,5 milijono kilometrų nuo Žemės.
Taip.
Vienam iš tų vadinamųjų Lagranžo taškų.
Kas yra labai keistas dalykas, aš nežinau, kad toks dalykas vis pirma egzistuoja ir tai pasirodo yra erdvė, kurioje šis tas teleskopas galės išbūti tokioj neliečiamai, kaip sakyti, būsinai, jis tai tam būna stabilus.
Taip, taip.
Lagranžo taškai yra padėtis kosmose, kuriuose tarp dviejų vienas aplink besisukančių kūnų, Žemės ir Mėnulio, bei Saulės ir Žemės, trečias atsidūręs mažos masės objektas, mūsų atveju James Webb kosminis teleskopas, gali neribotą laiką išbūti, nenaudojant jokių papildomų jėgų jo padėčiai stabilizuoti.
Kad jis yra, matot, čia dabar, jis toks labai didelis.
Jis yra be galo didelis, jis yra, galiu pasakyti, 100 kartų galingesnis už Hubble teleskopą.
Jo. Nors mes kaip sužinosim, jį dažnai lygina su Hubble teleskopu, kad čia yra jo, kaip sakoma,
pasiekėjas.
Pasiekėjas, bet taip nėra.
Iš kur yra visiškai kitas aparatas ir jo, jisai turi labai išskirtinį tokį dizainą. Origamis, jo. Nes užtruko 3 mėnesius, kad jisai išsilankstytų. Tai vis pirmai turėjo įvairiai sulankstyti ir nesinori daug pasakoti, nes visko papasakos.
Bet dar labai svarbu, kodėl ten reikėjo išsilankstyti, nes jis skrido į kosmosą Ariane 5 raketa, kaip ir sakiau, iš kosmodromo Europos kosmoso agentūros, buvo įtaisytas Smaigalyje ir mes, man atrodo, turim video, kaip jis ten kosmosą, žodžiu, pasiekė, kur atsiuntė būtent tas žmogus iš Nasos, kurį mes čia jau bandom.
Mums atsiuntė žmogus iš Nasos.
Jo. Ir, žodžiu, vien yra toks apsauginis ekranas, kuris apsaugo mokslinius instrumentus nuo Saulės ir panašiai. Jis yra maždaug teniso korto dydžio. Tai tokio į Smaigalį raketos niekaip nesukiši, kur ir buvo teleskopas. Tai reikia sulankstai, sudedi kosmose kažkaip įskrydį.
Ir patį teleskopą sudaro 4, galima sakyti, prietaisai.
Taip.
Aš jau žinau. Tai pirmasis yra NIRCAM-as. NIRCAM-as tai yra, galim sakyti, pagrindinės tokios kaip ir pirmasis teleskopo akis, kurisai galės aptikti šviesą. Bet yra problema, kad su šito būtent, jeigu jis būtų, tu negalėtum pamatyti, iš kur ta šviesa sklinda. Tai todėl yra reikalingas antras prietaisas, kurisai...
Koks jis?
Jis yra NIRSPEC-as, kuris parodys fizinės savybės. Tai būtent tos planetos, įskaitant temperatūrą, masę ir cheminę sudėtį.
Wow.
Yra trečias dar prietaisas, tai yra guiding sensor, kuris blokuos nereikalingą šviesą ir leis Webb teleskopui nurodyti tiksliai, į kur žiūrėti. Ir tas ketvirtas yra dar vienas labai įdomus, tai yra MIRI. Tai leis pamatyti per debesis į tolimą galaktiką, ko nepadarė, tarkim, Hubble teleskopas.
Ir biškinė taip veikia.
Ir biškinė taip veikia, bet kas yra įdomiai... Biškinė taip veikia. Kas yra įdomiai su MIRI, kad jisai labai... skleidžia didelę šilumą, todėl prie Webb teleskopo dar buvo pritaisytas toksai kaip prietaisas, kuris atšaldys MIRI, nes kitaip jis fiksuotų jo skleidžiamą šilumą ir tada rodmenys būtų neteisingi.
Taip. Labai gerai. Ir aš prieš tai šiek tiek paminėjau, kad šiaip ta misija kaip ir jinai ne tik buvo tapus tokiu kaip anekdotų bajeriukų tarp mokslininkų, bet dar ir turi tokių kontroversijų, nes James Webb yra buvęs Nasos administratorius. Administratorius tai yra paskiriamas dažniausiai prezidento dabar, pavyzdžiui, ir jis yra toks kaip direktorius visos Nasos, nes NASA turi daug centrų visoje Amerikoje. Ir James Webb, jis iš vienos pusės buvo mokslinės, inžinerinės pusės tikrai daug padarė, bet iš kitos pusės, dėl ko jį dabar kaltina tos kartos ir jaunesnės šiek tiek ir taip toliau, mokslininkai, kurie ten ir viešą laišką pasirašė ir taip toliau, kad jis palaikė homofobinę politiką.
Tuo metu jo homoseksualus.
Jo, ar jis buvo pats, kaip dabar Nature buvo atliktas tyrimas, nėra aišku iš tikrųjų iki galo. Kiek jis pats buvo homofobas, bet NASA ne visada buvo draugiška visiems skirtingiams žmonėms ir tuo metu, kaip James Webb dirbo buvo teismo sprendimas vienas dėl žmogaus, kuris buvo atleistas, nes jo vadovai galvojo, kad jis gėjus. Tiek užteko tuo metu ir kadangi James Webb tada buvo administratorius ir dar NASA ten biški sufeilino šitoj vietoj, nes pradžiai tarsi ir neigia, kad apskritai tokie dalykai buvo, tada išlindo, kad iš tikrųjų buvo, dar Nature atliko tyrimą, kur gavo kažkokius nulykintus susirašinėjimus NASOje, kur buvo svarstoma, tai aptarinėjama, ta vardo kontroversija. Tai dabar dėl to dažnai šita misija yra jau vadinama nebe James Webb Teleskop, o JWST.
Taip.
Tiesiog toks kodinis yra trumpam paliktas, kad kaip čia bus toliau. Ir
čia toks ne pirmas atvejis, NASA turėjo savo tokį, kaip sakyti, juodąjį momentą, tai ypač galbūt 60-aisiais metais, kada buvo apskritai labiau sunkiau žiūrima į kitos lyties, galbūt įdarbinimą arba bent jau darbo specifiką ir į rasę. Tai sakykime taip, kad NASA seniau buvo biški rasistai, net ne biški.
Ir seksistai, ir homofobai. Bet, jie palaikė tuometinę bendrą politiką, kokia buvo ta sociopolitinė situacija. Ir NASA, kadangi yra valstybinė įstaiga, jie, aišku, kad atstovavo tą sociopolitiką, kokia buvo tuo metu įteisinta. Ir segregacija buvo NASOje ir taip toliau. Ir dėl to dabar NASA iš visų jėgų stengiasi pataisyti tas klaidas ir yra labai pabrėžę savo tą įvairovės politiką. Nori per kitą misiją Artemis, kurios metu įsteigs Mėnulį nuolatinę kosminę stotį, kur dirbs astronautai, kad ten pasiektų pirmoji juodaodė moteris ir jau ten dirbtų ir taip toliau. Tiesiog stengiasi kiek įmanoma labiau būti atvira ir priimti skirtingų žmonių, nes tiesiog kai pradėjo lysti istorijos iš to meto, nėra labai gerai NASA'ai. Nėra labai, jie labai dirba daug ant savo įvaizdžio. Ir gal čia buvo tokia viena ryškiausių istorijų pastarųjų kelių metų su tokia Katherine Johnson.
Katherine Johnson yra Amerikos matematikė, kuri paliko neišdildomą įskiepį NASOje. Ji buvo viena pirmųjų afroamerikiečių moterų pradėjusių dirbti NASOje kaip mokslininkė. Katherine savo karjeros pradžioje NASOje užėmė žmogaus kompiuterio pareigas. Tai reiškia, kad jie atliko įvairius matematinius skaičiavimus prieš atsirandant specialiems skaitmeniniams kompiuteriams. Ji prisidėjo prie įvairių misijų. Jie apskaičiavo Alano Shepardo pirmojo amerikiečio kosmose skrydžio į kosmosą trajektoriją. Ji taip pat padėjo apskaičiuoti 1969 m. Apollo 11 skrydžio į Mėnulį trajektoriją. Jos darbai kalbėjo už save, todėl jos reputacija buvo stulbinanti. Amerikos astronautas John Glenn NASA's pareigūnams pareiškė, jog atsisakys skristi į kosmosą, kol Johnson nesutikrins skaičiavimų, kuriuos tuo metu atliko skaitmeniniai kompiuteriai. NASA's pradžioje moterims nebuvo leista skelbti savo vardų ataskaitose. Katherine Johnson buvo pirmoji moteris savo padalinyje, kurios vardas ir pavardė buvo paskelbti vienoje iš darbų ataskaitų. Jos talentas ir neeiliniai matematiniai sugebėjimai padėjo stiprų pamatą naujoms technologijoms kurtis.
Tai tokia labai graži istorija ir jinai vėliau gavo ir apdovanojimų įvairių ir buvo pagerbta už savo darbus, bet yra įdomu tai, kad pavyzdžiui, vienas yra labai National Geographic Society, ten, žodžiu, aukščiausias apdovanojimas, pamiršau, kaip jis vadinasi, jis jai buvo įteiktas praėjus 51 metams, kai buvo įteiktas Apollo astronautams, nes jinai būtent apskaičiavo ten ir Apollo ir taip toliau, bet kad ją jau pripažino beveik prieš jos mirtį, jinai 2020 mirė ir jai tos medalius ir apdovanojimus pradėjo jau šiais laikais dovanoti, nors jinai savo darbus padarė tada. Ir Obama ten buvo jos fanas, ten įteikė jai medalį ir panašiai. Ir tiesiog tai yra viena iš tų istorijų, kur parodo, kad nebuvo NASA draugiška Ir dėl to ir moteris astronautam negalėjo tapti, pavyzdžiui. Ir iki šiol, tai yra, bet jo, iki šiol. Bet vis tiek nebuvo toks didelis feilas, kaip moterim astronautėm tapti buvo labai sunku. Ir, sakykime, ten dar 70-metį jos negalėjo tapti astronautėmis be jokių priežasčių. Tiesiog jom atrašydavo, net ir, mes gal parodysim paskui laišką, atrašydavo, mes moterų kol kas nenorim kosmose ir maždaug neplanuojam tokių. Ir tos visos specialistės tiesiog būdavo atmestos. Kas yra, yra nesąmonė, tiesiog pusę populiacijos nurašyti be jokių svarių priežasčių. Ir jau, kai buvo pradėtos ruošti moteris skrydžiams į kosmosą, yra tokia astronautė Sally Ride.
Sally Ride buvo pirmoji Amerikos moteris kosmose, kas sukėlė nemažai naujų iššūkių Nasoje. Sally prisimena, kad Nasos inžinieriai paprašė jos padėti sukurti makiažo rinkinį, kurio jų manimų moteris norės naudoti kosmose. Pasak inžinierių, jie žinojo, kad vyras gali norėti skutimusi rinkinio, tačiau nežinojo, ko nori moteris. Bet didžiausias galvos skausmas atsirado sprendžiant menstruacijų klausimą, kuomet Sally Ride pasiūlė pasiimti 100 tamponų į savaitės laiko trunkančią kosmoso kelionę. Kaip teigia Sally, didžiąją dalį personalo tuo metu sudarė vyrai, todėl jiems tai buvo visiškai nauja sritis. Ji prisimena, kad spauda tuo metu jos išvykimą į kosmosą traktavo, lyg tai būtų neįveikiamas techninis iššūkis. Žurnalistams buvo įdomu, ar skrydis nepaveiks jos reprodukcinių organų ir ar ji verkia dėl esančio spaudimo. Visi norėjo sužinoti, kokią pudrą tepsiu ant veido, o ne ar esu tinkamai pasiruošus valdyti kosminę įrangą ir palydovus.
Aišku, dabar šita situacija keičiasi, bet keičiasi lėtai, nes ir dauguma tyrimų mokslinių apie tai, kaip kosmosas veikia žmogaus kūną, yra padaryta su vyrų kūnais. Ir maždaug 90% tyrimų tokių yra. Ir tik dabar, ir Europos kosmoso agentūra jau pradėjo daryti prieš keletą metų tyrimus su moters kūnu ir NASA jau planuoja daryti tyrimus, kad žinotume, kaip kosmosas veikia tiksliai moteris kūne. Šiaip moksle, beje, vyro kūnas buvo laikomas standartu. Ir netgi tyrimuose, kurie susiję su moters reprodukcinė sveikata, pavyzdžiui, su organais, kurių vyrai neturi, būdavo vis tiek tyriami vyrai. Čia yra tokia nesąmonė, yra tokių feilų, tu neįsivaizduoji. Bet vyriškas kūnas yra laikomas kaip standartu. Ir dėl to dauguma tyrimų ir su vaistais dabar jau taisosi, bet šiaip kas iki šiol yra atlikta, yra su vyrais atlikta. O moters kūnas, mes fiziškai skiriamės, norim to ar ne, ir žinai, mes turim, nežinau, organų, kurių jūs neturit, jūs turit organų, kurių mes neturim, mums kitaip hormonai veikia ir taip toliau, tai daryti tyrimus, laikant tik vieną lytį standartų, irgi feilas toks.
Netiška. Ir kvaila. Ir
šiaip tai mūsų sveikatą kainuoja, moterų sveikatą tai kainuoja, nes mes darom kažkokius dalykus, kurie yra patikrinti ant vyriško kūno.
Taip, o šiaip rekomenduoju pažiūrėti, yra geras filmas Hidden Figures.
Jo, arba knyga.
Ir būtent pasako tai, ką mes pasakojom apie žmonės kompiuterius, kurie atlikdavo skaičiavimus. Tik priminam, kad visus šaltinius, apie ką kalbam, galite rasti mūsų podcast'o aprašyme. Tad jeigu norit pasiskaityti apie keistus dalykus, kas vyko Nasoje, varykite į aprašymą. Taip pat nepamirškit paspausti like ir paremti mūsų kontribį, o dabar lekiam į pagrindinį šio podcast'o segmentą, tai yra pokalbis su John. Okay, so my first question is, how did you start working for the James Webb Telescope?
Okay, so 16 years ago, I was working on another mission that was doing global rain measurements, collaborating with the Japanese. And at that time, the manager of James Webb at that time, a man named Phil Sailbohouse, approached me and asked if I was interested in an opportunity on James Webb, helping him out manage the James Webb Telescope. So I knew what James Webb was about, and I said, that sounds very exciting. So I moved over back in 2006 and became the deputy technical for the James Webb Space Telescope, and I've stayed on since then.
How did you start working for NASA? Were you, when you were little, were you one of the kids who dreamed of being astronauts one day when they grew up, or it was just coincidental?
Well, I did grow up. I was during the Apollo program. I witnessed the moon missions, and I was always interested in space. I was good in math and physics, so I pursued an aerospace engineering degree, and then I looked for an opportunity to work for NASA. I didn't get it right out of college, but I took another job. But within 5 years, I was able to get a job with NASA. That was back in 1990. So I pursued it since I was young, just pursuing my interests, math and physics, which was engineering. I just followed that path and kept interested in space, and when I saw an opening at NASA, I applied for it, and I got it.
And I think everybody's interested because, NASA has this hype in society because we see NASA in movies and so on. How does your workday look like when you come to your office at NASA?
That's a great question. So, I basically took it for granted, but my wife, when I would come home from a bad day and complain about whatever technical challenge, she'd say, "You do know you're working for NASA, right?" I'm like, "Oh yeah, that's right. Yeah, that's right." So even my bad days are pretty good days. Yeah.
So you come to your office. What do you do then? You go to your engineering team. You reply emails. So what do you do?
So when my average day would come in, and then check the emails. In the heat of things, a couple of years ago, when we were in the heat of the development and building and testing, there'd be, at 9 o'clock in the morning, there'd be dozens, if not 100 emails. You go through that, and then we'd have a tag up with the team, engineering team, probably around 10 o'clock, and say, okay, based on what happened yesterday, are we ready to proceed with today, or the problems we had yesterday? Do we have any new information on that? So, I tackled the emails to get up to speed to what happened overnight, and then I'd meet the team, and they'd assess where they were, and then we'd discuss where to go for the rest of the day. And then most of my days were not prescribed. I'd come in and ready to react to whatever came about. And any given day, whether it's a problem, a technical problem, an engineering problem, or even a simple logistics problem, the size of this observatory made even moving it around the country and then over to Europe an incredible challenge. And the development inside the United States still required traveling various locations all around the country. So it was a matter of getting over those challenges, making sure even shipping, was a challenge. So anything could happen on any given day. And that was what was so fantastic about the job. There was no one day that was boring. They had challenges for sure, but it was not a boring day.
Wow. So you've been working with James Telescope since the day one, right?
No, I've since 2006. The day one would be about 2002.
2002, yeah. So maybe you know how the design of the telescope changed since the first sketches, because it's kind of unusual design for the telescope. Because we do imagine telescopes, in the tube and everything, and this one looks like a kite.
Origami.
Yeah, exactly.
So even in the early days, we knew when the scientists said what they wanted to do, we knew we had to have a telescope that was larger than the fairing of the rocket. So we knew we were going to build a telescope that was bigger than the rocket we were going to put it in. So we knew it had to be like an origami. That was even from the beginning. And that created the greatest challenge. The work changes in how many elements there were. We have settled with 18. At some stages, we had more than 18. The membrane, the sun shield looked a different shape. But over time, we had to optimize how to pack this the most efficient to be able to deploy it afterwards. So those trains happened from day one through our CDR, which is called our Critical Design Review in 2010. We made changes throughout that.
So is it true that you consult origami masters to know how to correctly fold the telescope?
No, I'm not aware of consulting origami experts on that necessarily. We just need to do efficient folding, like an origami, or like Hollywood would have the what are those things that fold into vehicles and fold out of transformer, like a transformer. We knew we had to do something like that. We did consult experts for some of the membranes and how to fold them better and stuff like that. I wouldn't necessarily call them origami experts, but they were folding experts. That fold things precisely.
What are the main goals of the mission, and what would be, so to say, your personal expectations from the James Webb Space Telescope mission?
What this mission is striving for is to see the first solar systems and galaxies that formed after the Big Bang. So that's basically the beginning of life.
Wow!
Right before that point, they call it the dark ages of the cosmos, where there wasn't enough energy for the elements to condense enough to create life. So we were going to go to the beginning of the phase of life, and I think that is just fantastic. So once you go to the beginning, and we are where we are now, we will see everything in between. So that means we will be able to see how conditions became unique for us humans to evolve and be here. And once we understand that, we can more intelligently look elsewhere in the universe where those conditions might be. So not only do we've heard about, the protoplanets or the exoplanets that are around Goldilocks regions around farther stars. There's many, many, many of them, and we would never be able to look at them all in a brief time. So once we understand the evolution of our galaxy, we can more accurately point to these exoplanets that are in galaxies that have a similar evolution, and then we would look at that. Now, our telescope will not be able to determine what's on those far planets, but it will be able to determine what's in the atmosphere of those planets. So if there's chemicals in the atmosphere that we associate with life, and there's obviously water, methane is a good one because methane is produced primarily by biological processes on Earth. So if we see methane in a distant planet's atmosphere, we can say some sort of biology is creating that.
Let's say we see some sort of biology, as you told, that was creating that on a very, very distant exoplanet. What's next? Because the planets are so far away and we don't really have technology to go and visit these planets. So what's next? Yeah, what would be?
So, well, we don't know how far or how near one of those planets are. We know some planets are very far away, light years away. It could be hundreds of thousands of light years away, or it could be just a couple of light years away. Our closest star is Alpha Centauri. That's 4 light years away. So still an insurmountable distance for us today. But if we come to realize that we're not alone in the universe, even if we can't visit those things, those beings, and say hi, to know that there's something else out there. That's
we are not
cool.
alone.
That's a lot. Maybe we'll get a bigger perspective of who we are, and maybe have a better view on things going on here. Maybe that's some of these things we fight about maybe are trivial, and we should get a perspective of, hey, there's things out there that
would be so nice.
But how do you know in which direction universe started? How do you know which direction you have to put the telescope to get the information?
To point. Yeah. So right now, the concept is that the universe is everywhere, expanding away from everything. So where was the origin? That's a philosophical conversation, I think, more than a science conversation. But how we do it is because of the orbit we chose, the L2 orbit that goes around the sun at the same time the Earth does. So in 1 year, we will go a complete orbit around the sun, and we will look away from the sun at all times. So in 1 year, we can look anywhere around. We can look the entire universe away from the Earth, and we're going to go around as a minimum times 5 times. So when we sit out there, we we have science programs that have been developed by the scientists. The world scientists have, there was a call out that said, okay, we got this great telescope, or we will have this great telescope. What science would you want to do? And so we had thousands of proposals of what to look at. And so there was a panel of scientists associated with the project that went through that thousands of ideas and picked, for the first year, picked a bunch. And they said, okay, we're going to look there. So that's what determines where we look at. We have these world-class scientists who decide this region of the sky out there, I think it holds a solution to this mystery of X or of Y. And they decide, yeah, that's a good place to look. So let's look there. So that's how we decide where to look. And we plan a year in advance. So the science we will do the first year had been selected 6 months ago. There'll be a call for new proposals on science in the coming months to select for the second year's science investigation. And then we'll do that again for the third and the fourth, and forever long we're up there. We keep every year getting new proposals on what to look at.
The mission itself had been postponed so many times. It's been postponed again and again and again and again. Have you ever lost hope? Because even before the launch at the end of last year, it was postponed for a couple of days. But again and again and again. I mean, it was like anecdotal.
Well, I will say it was disappointing and frustrating that we delayed. But being part of the process going on, we knew why they were being delayed. We were delayed for technical challenges. Early on, we were delayed for insufficient budget. That was incredibly frustrating because in the first 10 years of the mission, 8 years of the mission, there was just budget constraints that we were not able to complete the tasks that we were assigned to do. But after that, when it's technical problems, you're working through those technical problems and you're not focusing on, the frustrations of a delay. You're focusing on the challenges of solving the problem. So while it was very disappointing for everybody that we would have to delay things, it was, we never felt technically that we would not be able to achieve this. There was some concern that the policyholders or the people who provide the money, the taxpayers of the various countries, European countries or Canadian or U.S., would say, I can't afford this anymore, you have to stop. There was concerns about that along the way, but fortunately we continued to get the necessary support from our stakeholders to continue to fund us. And I think their patience is being rewarded with what we see in space today. It's the best telescope ever built. It far exceeds our requirements and even our most optimistic estimates. It's performing fabulously. So.
I can't wait for the results, for some fascinating pictures from space and so on.
Yes, in mid-July we're going to get some fascinating science pictures.
The components, the scientific instruments and the parts of the James Webb Telescope have to be space qualified, right? How do you test everything, and how do you make sure that everything that is built on Earth works up in space?
So we can replicate on the ground just about every environment except weightlessness. We can't do 0G. So we do a close approximation to that. So the launch itself is a very violent experience. You're on top of a rocket. There's a lot of sound and a lot of shaking. And then obviously space is very cold. So we create a test program for each component that launches, whether it's an instrument or it's just a beam, whatever piece of equipment that is going to be launched has to be exposed to the temperature it will see. And we shake it on vibration tables to replicate what it sees in the launch, on the launcher, on the rocket. And through those extensive testing, we are able to ensure that it won't shake apart when it's on the rocket on the way up. And once it gets there, it won't, the freezing temperatures won't cause any sort of binding because of this, and when things get cold, they contract. And things contracting, if you have little hinges, you got to make sure that when they contract, they don't get stuck. So we do all that on the ground. And then after we expose it to those environments, then we operate it. We say, either turn the instrument on and say, are you still working? Or if we're going to do a deployment after we expose it to the environment, we deploy it on the ground. Now the challenge is at 0G. So what we do, we push the physical ability, depending how big a piece is, and we sometimes turn it on its side. So the gravity direction is, like if there's a hinge that has to deploy, on the ground, has to deploy this way, then the gravity is pushing down on the hinge, and that's not the way it'll be in space. So we will rotate it over on its side, so now gravity is this way, and we operate the hinge this way. So basically the hinge that is here, now the gravity is no longer playing a big part on it. So we try creative ways to come up and try to address a 0G environment. Some other ways we do is, if we have a hinge this way and it's too big to rotate this way, we have some cabling that we use to have essentially, it could be a balloon, a helium balloon that would offset it as it rises, or it could be just a pulley system with a weight that matches the weight of the device, so it feels like it's 0G. That's the biggest challenge in the testing we do, is how to replicate the 0G, weightlessness of space. And we had extensive programs to do that, especially with the cables, where the cables float around. We had to do some very fancy testing, as well as some attach points on the cables to hold them in place while it goes through that environment.
A couple of weeks ago, we were talking to Professor Charles Zalachi of NASA JPL, and he was telling us about the 5 minutes of horror or terror, whatever you call them.
Right.
It's before when a spacecraft enters or lands on another planet.
Right.
Did James Webb, or has James Webb had its 5 minutes of horror?
Yeah. JPL calls it 7 minutes of terror when they arrive to a planet until it lands to the ground. Yeah. And ours was really 2 weeks of high anxiety, because exactly. So when we launched, that starts the high anxiety, and then when we completed our deployments 2 weeks later, that entire period was our corollary to their 7 minutes of terror. So,
Jesus, how did you survive?
It was interesting because we tested and we trained extensively, so we felt confident, but we couldn't feel comfortable. So we essentially, whenever we send a command to the spacecraft, unlike interplanetary missions where it could take minutes before you see the spacecraft, or actually more than tens of minutes before you see a response, we could see it responses, in seconds. So we didn't have to wait so long. But whenever we sent the command to do something, we have data on our computers that'll tell us what the spacecraft is doing, and there'll be numbers of metric mnemonics that tell us the condition, and they would, if they were causing problems, those mnemonics from a green number would turn to a yellow number and then to a red number. So we'd stare at the monitor with all green numbers. We'd send the command, and we'd we'd wait with bated breath as we make sure none of the green numbers went to a different color, or if it did go to a yellow, what did it mean? And then it would recover. So for the most part, we never saw a red number, which means it never got a problem. We did see a yellow state at one point, and we had to pause and say, what is that telling us? And, after a few minutes of discussion, we realized that that's okay. The fact that it's yellow doesn't mean these are conditions that would make it yellow, and we're okay with that condition. So it was incredibly smooth. But in training, we had red numbers come up all the time, and so, we got to figure that. How can we work around that problem? But in real life, no reds. It was pretty spectacular.
Great.
That's great. Wow.
How many tests you do on specific part to know that you are ready to launch?
What we typically do is we test before we do performance tests on it to make sure the instrument's right. Then we expose it to whatever the environment, the shaking, the cold, and everything else. And then we turn it on again for performance afterwards. So we do at least 2, one before and one after. And through our long years of testing, we've had many times where we've been unsuccessful post environments getting it to work the way we wanted to. So we'd have to take time, figure out what went wrong, correct what went wrong, fix it, and then go through test, shake it up, expose it. We call it shake and bake. We shake it, and then in this case, it would cool it, but we shake and bake it, and then we would test it again. So we've done that several times on big components. The sun shield, the big solar sail that we have up there that protects us. We had to actually do that on the ground. We had to do 3 different deployments of it. So we had tests, we checked the performance, we shook it, and we tested it afterwards, and we had a problem we had to fix. And we did it again, and we had to fix it again. So we did that 3 times on the ground, and that was, you know, we reaped the benefit of that, because after all that testing, it worked perfectly on orbit. But on the ground, that exposure, you know, told us how delicate this piece of hardware is, and we got to really pay attention. And just like a parachute, the most important folding of a parachute is the last time you fold it before you use it. And so that's the critical thing. And that's why trained people can only do the folding of a parachute, or yourself, so you can know what's going on. And we made sure the last fold of the sun shield, we paid extreme attention to that it was folded just right. So when it got out there was no cables twisted or anything like that. And so it worked out very well.
Is it true that most of the scientific instruments of the James Webb Space Telescope were complete some 10 plus years ago? And if that's true, what was the reasons why the mission was delayed and postponed so many times?
Excellent question, complicated one. So when we started this development, there were 10 technologies that needed to be invented, and so for it to be realized. When we started this, the detectors we use in orbit didn't exist. The mirrors that you see, the technology for those mirrors didn't exist. And there's the instruments, some of the instrument components, the cooler, for example, the ability of the cooler didn't exist. So in the beginning, we focused we didn't have a lot of resources at the beginning of the program. So we focused our limited resources on those things that were technological challenges. And that was the telescope itself, the sun shield was a lesser degree, and the spacecraft was delayed because that was not a very unusual. The spacecraft bus, the thing that provides the power and the control, that was delayed a little bit consciously to focus energies on the near-term stuff. So the instruments were started right away, the telescope was started right away, the sun shield was delayed a little bit, and then the spacecraft itself was delayed a little further. So for the first 8 years of the development, all energy and attention was focused on the instruments and the telescope. Then we picked up on doing the spacecraft. So there was a little out of phase to begin with, because we couldn't afford to do everything all at once. And then each one of those items, the technically challenging ones and the spacecraft, which was not so technically challenged, all had their own problems. But the instruments, they were able to recover the problems, and they focused. So they delivered, in support of a 2014 launch date. At the time, that was when they were targeting for 2013 launch date. That's what they were targeting for. But the and the telescope also was able to meet that schedule. But the sun shield and the spacecraft had their challenges. And so the instruments delivered, the telescope was ready, and it took the spacecraft and the sun shield additional years to recover what we basically were dealing with. So that's why, and the instruments, the first instrument was delivered in 2012, and the last instrument was delivered in 2013. So it's very unusual for the instruments to be left on the ground that long. Because we design these things to operate in space. That's where they like to be. That's where they want to be. So on the ground, we had to take special care for the telescope and the instruments while they're on the ground to make sure that, the moisture didn't get in there and do any corrosion. That
it raises the costs of the whole mission itself, right? Keeping the instruments on the ground.
Right. I mean, it certainly cost-wise, it costs more to be everything on the ground. So the instruments, after they were delivered, they had very little additional cost compared to the cost for building the spacecraft and the sun shield. But it had a cost on, it could have a cost on, how long it's on the ground. Does it take away from its on-orbit life? So far, the instruments look exactly like they did when we last tested them. So the instruments are in great shape, but there was a risk that, moisture got in there while it was sitting on the ground, or, just as it ages, lubrication might have evaporated, but all indications say that that's not the case. So the biggest cost, or the longer everything was on the ground, the bigger the cost there was. So, so the cost is very large, You know, the number for getting to launch is $9 billion, and over $9 billion over 20 years, that works out to about $450 million a year. Still
Worth it.
a lot of money, right? However,
Oh, yeah.
are you familiar? You're familiar with American baseball, right?
Yeah.
So the payroll for the New York Yankees and the Boston Red Sox is $450 million a year. So JWST spent average per year the same as it costs to put 50 men on a playing field for 9 months of the year to play a game. So cost is relative. What we're going to get out of James Webb with the advancement of knowledge and the inspiration of the next generation to strive for greater things, I think it is a reasonable investment compared to, I'm not saying the Yankees and Boston are not a good team, but you know, spending that money is going to benefit a couple million people. Spending that money and get JWST, you benefit all humanity. So you just have to put things in perspective, and yes, a lot of money, but we get a pretty good return on our investment.
As I understand correctly, sun is the biggest enemy to the James Webb Telescope because of the radiation and light coming from the sun.
Yes.
Yeah. So, how strongly will the light from the sun and the space radiation will change the quality of the information which we will get from the James Webb Telescope?
So, good question. We designed it knowing that the sun will always be there, and so that sun shield, we designed the sun shield capability. It's a thermal isolator from the sun, so it's doing fabulous. We have plenty of margin today, but we designed it so that radiation will degrade the material of the sun shield over time and cause it to be less thermally good. So we designed it such that after 10 years, it's still thermally good. We've got enough margin in it to make that happen. So, so that's how we kind of designed things. We say, okay, we know it's going to be a hostile environment out there. So, and we want to last for 5 or 10 years. The instruments are designed for 5 years. The propellant is designed for 10 years, and some of the sun shield material is designed for 10 years. So we design those things to take into the fact that they will degrade over time. And engineers are always conservative. So basically, even though you tell them, okay, you only need to design for 10 years, they have hidden margin, and it usually goes more than that. So just like the rovers, the first rovers, Opportunity and Spirit, were a 90-day mission.
Like the Voyager mission.
So we just, that's how we came for it.
This is the beautiful thing with space exploration, that usually engineers and scientists somehow you are ahead of time, and that is really really beautiful. James Webb has been called the successor of Hubble Space Telescope, and I think I even used this analogy when I was talking about James Webb Space Telescope, but this isn't really scientifically correct, as I understand. What do you know a better analogy to the mission?
So James Webb is not the successor to Hubble. It is the complementary to Hubble. It basically will increase our knowledge of a spectrum. The replacement to Hubble is actually being developed now, and that's called the Roman Space Telescope. That one will actually do what Hubble did, but do it more refined and with higher quality. James Webb, you know, Hubble works in the visible, so it has only a little bit of infrared, but it's mostly the visible light. And James Webb takes that knowledge and goes from the infrared and takes it much further into the infrared. So it's a complementary sister to Hubble. It basically expands our electromagnetic spectrum knowledge more.
When do we expect the first results of James Webb Telescope? Because right now, telescope is in the deployment, right?
No, the telescope has been deployed. It was successfully deployed in the first week in January. It finished. It's going through commissioning. So we have released some pictures recently of what the telescope can see, and we've used those. And we can certainly provide you those pictures if you don't have them. But we even released some just Monday, and
I saw.
Yeah. So those are engineering pictures, if you will. We look at a star because we needed to line a telescope. So we looked at a bright star to line a telescope, and those are the images we saw. So in 8 weeks, in I guess it was, let's see, mid-July. So where are we now? April. So about 10 weeks, we will release our first science images. We will finish the commissioning of the observatory in 8 weeks. By the end of June, we will essentially complete our commissioning, meaning that the telescope itself is ready to rock and roll. And then 2 weeks later, in mid-July, we will release our first science images. And we haven't taken them yet. We'll start taking those in the next couple of weeks. But I can assure you, the scientists are beyond excited. These pictures will be spectacular. We don't know what they are. They're not telling us what they are, what those images are of.
You don't know that as well? You work for the team and you don't. Wow. How? I couldn't bear it. I couldn't bear it. We know that NASA plans decades in advance, and a couple of weeks ago there was this report, NASA Decadal, published with recommendations coming from scientists and engineers from different fields. Does James Webb have a successor since you plan decades in advance?
Yeah, excellent point. So in the decadal study, there was a successor, one that is more capable than James Webb. And that one, along with everything that was in the decadal study, was agreed to go on for further investigation, further study. So it will be, James Webb will be able to look at the atmospheres of distant planets, know what's going on there. The successors, depending on the technology, hopefully will do a better job once we identify planets that might have biology on it, like we talked about the other day. The next successors hopefully will be better able to understand what that biology, at least, we will see light that was billions of years in the past. So what biology was there at the time? Obviously, it's not what's there instantaneously today, but what was there at the time when the light was emitted from it. So, and that one probably, that telescope doesn't have a name yet, but it probably, if it's approved along the way, it'll be launched probably in the mid-30s.
How big it should be.
Oh yeah, and how much it will cost.
Yeah, because James Webb is gigantic in comparison to other space telescopes. Yeah. So this successor, how big?
Yeah, how big are the mirrors gonna be?
Yeah.
Yeah, so James Webb is a 6.5 meter diameter. The telescopes they're talking about are greater than 10 meters. And how big each individual element will be an engineering challenge. They know the size of the entire light bucket they want, and that's greater than 10 meters, I think, is what last I heard. And they would optimize what size. They could use the same size individual mirror like we have and just have more of them, or they can make bigger ones. Those are going through part of the study phases now, the engineering optimization, and they'll be doing that study for the next 5 or so years until they're ready to begin implementing it.
And, is there any theories of how the Big Bang started, maybe?
Of the universe. Other than the Big Bang.
Yep.
Well, there are many theories on beginning of the cosmos, and that's more philosophical because nobody knows for sure. We can only go with the data we draw, and right now, the data we have from COBE and WMAP tell us that the theory of the Big Bang is the most plausible one today. But I will tell you, from the images that we sent out already, we looked at a star, and it was released, I guess, about a month or so ago, and we can get you the image. I'm sure Thaddeus can follow that up with you. We looked at a star in what we thought was a relatively dark point of the sky. And when we resolved the image, we saw over 250 galaxies around that star. Wow. So those are the galaxies that have never been seen before by humans. And so we know with this telescope that our capability is so great that everywhere we look in the sky, we see galaxies. They're almost in the way. There's so many galaxies. So our theories will have to be rewritten, just like they were when Hubble was launched. They'll have to be rewritten once the James Webb data comes down. We already know that we're going to see things we didn't think were possible because of just the capability of this telescope. we're going to see to the beginning, whatever that beginning is, I don't know, but we're going to see to the beginning of light because we have that much capability based on the theories today.
I can't believe this is all happening in our lifetime. It's just unreal.
Yeah.
Can you explain us, John, one more time how pictures are taken by the telescopes?
Any object emits photons, and so we have photons that are, hitting our eyes and resolving the image on the computer is coming from a photon emitted from the computer. So these photons are everywhere, and so I'll tell you how sensitive we are to the observatory, and then we'll get into how we take a picture. So for you to resolve an image right now, you're seeing millions of photons in your eyes, and that's how you're resolving me on the screen, as you're seeing millions of them. And so how sensitive we are is James Webb only needs tens of photons. If James Webb was sitting on the surface of the Earth and looking at the crescent moon, the dark side of the moon, if you ignore atmosphere effects for the moment. So you're looking up there, and if somebody was to light a match on the crescent part of the moon, say, or turn on a nightlight, James Webb will be able to detect it from the surface of the Earth.
Okay.
So we can see the thermal image of a bumblebee. If a bumblebee was on the moon, we would be able to resolve that. We can see tens of photons and resolve the image. That's how sensitive we are. So how we take images is you go out in space and you look at a star. That star is emitting photons. You see those photons in your eyes. That's how you see the star. So the larger your eyeballs, the more precisely you would see a star. So that's the aperture. So the scientists know that principle, and they said, okay, I want to see back to the beginning. We think the beginning is here. To do that, I think I have to be as sensitive as an engineering number that means nothing to the layperson, but very sensitive, that you and I could never see. In order to make that happen, how many photons would I need for the detectors to sense it? And they say, oh, you probably need tens of photons. Okay, so how big does the telescope need to be to give that detector tens of photons? And they said, well, we know from other scientific investigation that how many photons from various distances are out there in space. So they say, well, I think I need a 21 foot diameter or 6.5 meter diameter telescope. We call it a light bucket. A bucket so big, you can see my hands, bucket so big that these tens of photons would be captured. It lands on the big dish you see. And then on a tripod in front is another convex mirror that the photons bounce off that secondary mirror and then go down to the center of the telescope to the detector planes of the instruments. And so those principles are also why we essentially have an extremely precisely cleaned mirror and extremely precisely polished mirror. Because any dust particle that's on that big gold mirror that you see would cause a photon, if it struck it, to miss the secondary mirror. And that would be disappointing. If a photon that's been traveling since the beginning of time hits our mirror, we would hate to miss it going off the secondary. So we have a very incredibly precisely cleaned and polished mirror. The surface of the mirror is very smooth. If you were to expand that mirror, that one density, one of those elements, which is about a meter of mirror, if you would expand that mirror from 1 meter to 3,000 miles, the highest point on that 3,000 mile face would be 2 inches. That's how precise. It's in nanometers, which is, 10 to the minus 9 meters is the height of that actual thing.
What kind of technology you use to polish the mirrors? Because it sounds like technology from the future.
Well, remember I said that we had to develop technologies. One of them was the mirror. So what we did is we picked beryllium, which is a metal. Over Hubble had a glass mirror. And we were doing a trade between glass and beryllium. And we chose beryllium because of it's a little more mass efficient, means that we can make it lighter, but also it is incredibly stable. So what we had to do with these mirrors is we took the beryllium metal and we polished it with special machines, polishing machines that had to be invented to precisely smooth it out. And because all metals and most materials will change shape as they go through temperature, we had a problem. Well, we're going to polish it at room temperature, but we're going to fly it at minus 250 C. So how are we going to do that? So we had to develop the prescription. Well, first of all, beryllium is very repeatable. We know how it changes shape over temperature. It is very precise. If I make it, if it's this shape in room temperature, it'll be that shape in cryo. We can repeatedly do that. So what we had to do is we had to perfectly polish these mirrors incorrectly on the ground so that when it got in space, it would change shape to be precisely in prescription. Wow. And so we had to do that. That's part of the first 8 years of this mission. I was talking about technology development. We had to test out how to make that happen, test these, polish these mirrors, put them in a thermovac chamber at temperature, check the surface finish, realize where we were wrong, fix it. We did that over, each mirror element took 4 years from beginning polishing to finishing, as we polished it precisely, incorrectly, and then predicted it correctly how it would be.
It now makes sense. When you're telling all these details, it now makes sense why the telescope, it took so much time to build it, you know?
And our last question, Todd told us that you are retiring soon, right? What are your plans next, and are you going to keep an eye or a hand on the mission? Because probably it should be difficult to let it go, because for we are not related to the mission, and we are fans of the mission, so to say.
I'm so glad you're fans, because it's bittersweet that I am retiring. I'm 60, so it's a good age for me to retire. And but you know, on the one hand, this is the pinnacle of my career. No other mission will be as exciting or as challenging. So it's a little bit, what would I do next? That would give me the same kind of feeling. It's pretty hard to figure out, but it's the best thing to go out on. And but I'm not necessarily going away. You know, there's a community here. We've worked together for long. After we launch, all of us who are leaving the mission, some stay on through operations for the next 5-10 years, but most of us who are in development move on, and every one of us goes through a mourning process of, you know, you're losing something that you spend so much time with, and so there's grieving, you know, grieving-like experience that you have to deal with, and we're all going through that, but we will stay in touch. And I personally know the people who are running this observatory, and so I will personally be able to stay in touch and keep in touch with the what's going on and stuff like that. So that's critical for me feeling better about moving off onto something else. I'll stay in touch, and I'll be able to have a inside track maybe on what's going on, because I'll know the people who are here still after I go.
Wow. Thank you for your time, for the second chance you gave us. It's we really appreciate your time, and well, every time I read the news coming from the mission, I'm impressed. I saw even from the picture that you used to calibrate the cameras.
Oh yeah.
At first it was a couple of stars, then it was 1 star. I was amazed then. It's just, I wish you the best of luck, and thank you for doing what you do, and for inspiring generations in the future to explore space and look up the sky, right?
Yep, thank you so much, John.
It is my pleasure. I hope you can see the pleasure coming through. I love talking about it, so I'm glad we were able to schedule again.
Džonui patiko su mumis kalbėtis, tikimės, kad jums patiko mūsų klausytis. Būtinai pasidalinkite epizodų su draugais, būtinai paspauskite like ir leiskite YouTube algoritmo dievams iškelti šį epizodą kuo aukščiau. Na žinoma, jeigu patiko mes, tai visada esat laukiami pasiekti mus mūsų Instagrame. O dabar sakom iki.